Apologies, I had to switch locations. Let's carry on. The next proof of the Nullstellensatz is via Jacobsin rings. And Jacobsin rings were introduced in order to prove the Nullstellensatz by Wolfgang Krull, who's pictured on the left. And he named them in honor of Nathan Jacobson, who was a commutative algebraist in America. Wolfgang Krull was, the paper was published in 1951. Krull himself had been, just a few years prior, a member of the Nazi Party, and Jacobson was a prominent Jewish mathematician in America, which goes to show how complicated history can be, even the history of mathematics. But let's carry on with the proof. First, we'll define Jacobsin rings. So we say, let A be a ring A is called Jacobson if every prime ideal is the intersection of the maximal ideals containing it. Okay. An equivalent characterization would be that every prime is the intersection of the prime ideals strictly containing it. Sorry, I should say every non-maximal prime is the intersection of primes strictly containing it. Okay, and now we can state the Jacobson version of the Nullstellensatz. Let A be Jacobson, and let B be a finitely generated A algebra, then B is Jacobson. Furthermore, if n in B is maximal, then M equals n intersect A, the maximal ideal intersected with the base ring, is maximal, and B mod n is a finite extension of A mod n. Okay. So, not obvious at the outset how this implies the Nullstellensatz, or why it should earn the name Nullstellensatz, but we'll see after proving this that indeed it follows quite simply. Okay, let's start by proving a quick technical lemma. The following are equivalent. First, A is Jacobson, and second, for any ideal P in A prime, if B is a non-zero element in the quotient ring A mod P, and it has the property that B adjoin B inverse is a field, then B is a field. So let's show first of all that the first condition, that A is Jacobson, implies the second. So take P in A prime, A mod P is an integral domain furthermore, it's Jacobson because of the correspondence theorem. The fact that it's an integral domain means that 0 is prime. And the fact that it's Jacobson means that it's the intersection of all the maximal ideals. Okay. Meanwhile, if we have B not equal to 0 in B, which is A mod P, with B adjoining B inverse, a field, then what that means for us is that any non-zero maximal ideal in B must contain B. So any non-zero max ideal contains B, because otherwise when you add in B inverse, the ideal will stay proper. But if every non-zero maximal ideal contains B, then B should be in the intersection of all maximal ideals, which means that B should be in the zero ideal, which is obviously against our assumptions on B. So that means that there are no non-zero maximal ideals. Which is enough to tell us that B is a field. Okay, now let's consider the other direction. So we're going to look at 2 implies 1. In order to show that the ring is Jacobson, we want to show that for any P contained in A prime, we have that P is equal to, we want to show P is equal to the intersection of M maximal such that P is contained in M. Okay, well, how would we go about showing that? We're going to suppose the opposite and deduce a contradiction. So suppose not. Okay, so we have Q equal to the intersection of all of the M maximal containing P, and this is not equal to P. So we can find some element F in Q minus P. And we can find, using Zorn's lemma, we can construct a maximal prime ideal containing P and not F. Okay, so we want to find the maximal element of this set of ideals. This will exist by Zorn's lemma. So we have a maximal prime ideal containing P and not containing F, but we know that this can't be a maximal ideal, so let's call this P. We know that P can't be maximal because we already said that F is in all maximal ideals containing P. So P is not maximal. But so what does that mean in terms of A mod P? Well, A mod P, if P is not maximal, must be not a field. Okay. On the other hand, what happens when we adjoin F inverse? But because we chose P to be maximal with respect to not intersecting F, that means that P is maximal in the localization at F, adjoin F inverse, which means in particular that when you quotient by P and then you adjoin this element, this will be a field. Okay, and that contradicts our property 2, so it must be that from the beginning P was in fact equal to the intersection of all the maximal ideals. Okay, so that's our lemma. Now we'll start proving the Jacobson Nullstellensatz. So again, what are we trying to show? We want to show that B is Jacobson and B mod n is a finite field extension over A mod m. okay, where M is the intersection of N with A. Okay, so let's take this case first. The case is where we have a field and a transcendental element adjoined, so it's just a polynomial ring over a field in one variable. So we know that the primes of this ring are just the zero ideal, and the ideals generated by a single monic irreducible polynomial. Okay. So every non-zero prime is maximal. So to check Jacobson, all you need is to check the zero ideal. The zero ideal is the intersection of all of the maximal ideals. Well, this would be true as long as we have infinitely many. So if there are infinitely many maximal ideals, then 0 will be equal to their intersection. The reason being that if you have a finite set, then the product of all of the generators will be in their intersection. But if you have an infinite set, there's no polynomial which has all of those irreducible elements as factors. So you're left with just 0. Okay, but we can say that M will always be infinite because there are infinitely many irreducible polynomials, and you can use Euclid's argument. Euclid, suppose you have a finite list, f1 through fn are irreducibles, then just take g equals f1 up to fn plus 1. G must have a different irreducible factor. Okay, so that tells us that we do have infinitely many maximal ideals, which tells us that 0 is the intersection of those maximal ideals. So far we've proved that B is Jacobson. To prove that B mod n is finite over A mod m, well, m is equal to n intersect A, which is just going to be the 0 ideal in every case, because the only maximal ideal of a field is the 0 ideal. And B mod n, we can tell is because it's just an extension by a variable that satisfies a monic irreducible polynomial. It's an integral extension, so it's a finite algebraic extension. Of A. Okay, so that covers the case where A is a field and X is transcendental. The next case is where A is not a field, A is any Jacobsin ring, and X is still transcendental. So again, we want to show B is Jacobson, and B mod n is finite over A mod m. So we're going to use the lemma formulation of the Jacobson property. So we're going to show that B will have this property. So take any B in B with B not equal to 0. Suppose B adjoin B inverse is a field. Okay. What does that mean for us? Then A adjoin X, B inverse is a field just by definition of B. But if A adjoin X adjoin B inverse is a field, the same could certainly be said to be true for K adjoin X adjoin B inverse, where K equals frac A. Frac A. So certainly this would be true. But we know that K adjoin X, by the first argument that we just made, will also be Jacobson. And that implies that K adjoin X B inverse being a field implies that K adjoin X is a field. But this is impossible, since a polynomial ring over a field is not a field. This means that it must be the case that A adjoin X, or rather B adjoin B inverse, is not a field. So the condition is true vacuously. So B is Jacobson. Okay. Now let's consider the case where B is equal to an extension of A, a Jacobsin ring, but that it's not a transcendental element. There's some algebraic relations on X. Okay, so B, again, we want to show that B is Jacobson. And that B mod n is equal to, is finite over A mod m. Okay, so the fact that A adjoin X mod Q, so B equals A adjoin X mod Q. Again, we're using the lemma formulation, so if we have, so take B in B not equal to 0, we're going to adjoin BB inverse and suppose it's a field. Okay, so suppose B adjoin B inverse is a field. Then consider B adjoin B inverse as, so this is going to be equal to A adjoin X modulo Q A adjoin X. And then we're joining B inverse to that. So this is going to be a finite field. This is going to be an extension of K adjoin X mod Q K adjoin X. Okay, because this is just taking the fraction field. So once you're looking at the fraction field, so QK adjoin X is going to be a maximal ideal, which means that the quotient will be a field. Since we know Q is a non-zero prime ideal, when we multiply it by a polynomial ring in one variable, we're going to get a maximal ideal. So this is a field. now that we have an algebraic extension, we know that there's some relation in Q that the image of x will satisfy, so that's Pn x to the n plus Pn minus 1 x to the n minus 1 down to P0 equals 0. So what that means for us is that B adjoin Pn inverse is integral over A adjoin Pn inverse. So similarly, looking at B inverse, well, we know that B is in B, so that implies that we have, by the fact that we have this algebraic extension, we're going to have some polynomial relation satisfied by B, so Qn b to the n plus, let's make it Qm b to the m plus Qm b to the m minus 1 down to Q naught equals 0. Well, if we adjoin Q0 and then we clear, we divide by a high enough power of B, what we'll get here is B inverse to the m plus Q1 over Q0 B inverse to the m minus 1 plus down to Qm over Q0 equals 0. So that means that B inverse is integral over A adjoin Q naught, but we also want to keep Pn inverse in there. So we're going to take Pn Q naught inverse. Okay. So we already know that B adjoin B inverse is a field, so what we have is an integral extension of integral domains. The top one is a field, so that means the bottom one is also a field. But we know that A is a Jacobsin ring, so if you adjoin the inverse of some element and get a field, then that means that the original, and just taking the prime ideal that you're quotienting by to be the zero ideal, which we should have. So that gives us that A itself is a field. But if A itself is a field, then B equals A adjoin X mod Q. This is an integral extension of a field. So that means it's also a field. Okay. So we found that indeed B adjoin B inverse is a field implies that B itself is a field. So this gives us the result for A adjoin X mod Q, so just generated by a single element. And now let's consider where we generate by a bunch of elements, finitely generated. So we have A prime equal to A adjoin x1 through xn minus 1. This will be Jacobson by induction hypothesis. Then A prime adjoin xn, this is just an extension of a Jacobsin ring by a single variable, so this implies that this is also Jacobson by the n equals 1 case. So that confirms that it's Jacobson. To get that it's that we have the result regarding maximal ideals. So if we have a maximal ideal n in A adjoin x1 through xn, then using the base case, we have n intersected with A adjoin x1 through xn minus 1. That's equal to m, and we know that n, or rather b mod n, is finite over A mod m. Sorry, A adjoin x1 through, let's call this A prime mod m. But then A prime mod m is also finite over A mod m. A mod, let's call it O. So if just the maximal ideal intersected with the ring A. So that implies, by transitivity of finite extension, that implies that B mod n, is also finite over A mod O, which gives the result. Okay, so we have that it's Jacobson, and that B is Jacobson, and that this finite extension property holds. How does the Jacobson version imply the standard Nullstellensatz? So again, the Jacobson version is that if you have A Jacobson and B a finitely generated A algebra, then B is Jacobson, and you can also have this property of the extensions. B mod n is a finite extension of A mod m. Okay, so that's one. That's the Jacobson version, and we eventually want to get to the standard version, where K is an algebraically closed field and I is an ideal in the polynomial ring with n variables. Then I of v of I equals radical of I. Okay, well, so the proof is as follows. First of all, K adjoin x1 through xn. Because K is a field, which means it's Jacobson, so is this. This is Jacobson. Okay, when K is algebraically closed, that means that V of I is equal to the set of maximal ideals containing I. But because this is a Jacobsin ring, the set of maximal ideals containing I is equal to the intersection, and I of V of I is the intersection of all of those. This is the intersection of the maximal ideals. But because I is Jacobson, because this ring is Jacobson, the polynomial ring is Jacobson, we have that the intersection of maximal ideals is equal to the intersection of the prime ideals containing I, but the intersection of the prime ideals containing I is exactly equal to the radical of I. Okay? That shows that the Jacobson version of the Nullstellensatz implies the standard version, and we might see some additional proofs of Nullstellensatz later in the class, later in the semester, but for now I think that's it. Thank you so much.